The surface around us seems static and dead, except for when it suddenly vomits out angry, viscous lava and spontaneously cracks open following a maelstrom of rock. What is the driving force behind these mysterious phenomena, and can we prepare for them? The layers of the Earth. The Earth is structured like a giant onion, with different layers corresponding to different chemical compositions, properties, and structures. Let's peel the layers off one by one. The Earth has a thin crust draped over a viscous mantle, with a liquid outer core inside it, surrounding a solid heart of the inner core. The crust is 40 kilometers thick and constitutes around 1% of the planet's entire mass. It is composed of a blend of different solid rocks and minerals, composed of elements including oxygen, silicon, aluminium, iron, calcium, sodium, magnesium, potassium, titanium, hydrogen, and others. In general, the denser oceanic crust that composes the seafloor is made out of sema, silica, and magnesium, while the lighter continental crust is composed of Cl, silica, and aluminium. The temperature of the crust varies from the surface to the boundary between the crust and the mantle. At the surface, the temperature depends on the meteorological conditions. For instance, it may plunge down to negative 80 degrees Celsius in the Antarctic winter, while it may soar up to 50 degrees Celsius in the Sahara Desert. However, down where the crust meets the upper layers of the mantle, the temperature climbs up to over 400 degrees Celsius. The boundary between the crust and the mantle is known as the Mohorovičić discontinuity, or the MOHO for short, approximately 40 kilometers down from the surface, and marks the rapid increase of seismic waves. The mantle is the thickest layer of the Earth, composing 84% of its total volume with its 2,900 kilometer thick structure. It is mostly composed of silicates, such as garnet olivine and pyroxene, in addition to magnesium oxide, iron, aluminium, calcium, sodium, and potassium. Temperatures vary from 1,000 degrees Celsius at the MOHO to 3,700 degrees Celsius near the Gutenberg discontinuity, the core mantle boundary. The crust and the uppermost 60 kilometers of the mantle are collectively referred to as the lithosphere, which spans 100 kilometers underground and is where all the tectonic activity occurs. Below the lithosphere is the asthenosphere, which extends to around 410 kilometers down. Owing to the high temperatures, rocks partially melt, forming a viscous, angry fluid that drives around the lithosphere above. Beneath the asthenosphere, from 410 kilometers to 660 kilometers down, lies the transition zone of the mantle, and is demarcated by a sharp increase in density of rock. The increase in density effectively prevents mixing of material from the upper and lower mantle, and vice versa, and prevents the lithosphere from sinking further into the mantle. The transition zone also contains an abundance of water in the form of hydroxide anions. The mesosphere, the lower part of the mantle that extends from 660 kilometers down to 2,700 kilometers, is hotter and denser than the upper mantle and the transition zone, yet the layer remains a superheated solid due to the immense pressure exerted upon it. Underneath the mesosphere is a relatively thin layer of the mantle with bizarre properties known as the D double prime layer, which is around 200 kilometers thick and extends down to the Gutenberg discontinuity. As of now, the layer is surrounded by mystery as scientists are struggling to understand and answer questions such as why the composition of the layer is the way it is, but the layer promises to reveal clues to how the mantle interacts with the core. The outer core is 2,200 kilometers thick, and it is composed of alloys of nickel and iron, along with other compounds that dissolve inside of nickel and iron. Due to its fluid nature, the outer core is easily deformed, and changes to its shape are the cause of the magnetic field of the Earth. temperatures can range from 4,500 degrees Celsius to 5,500 degrees Celsius. Below the Bullen discontinuity, the border between the outer core and the inner cores, and the hottest point in Earth, the inner core stretches 1,200 more kilometers to the center of the Earth, with an average temperature of 5,200 degrees Celsius. Unlike the outer core, the inner core is a ball of solid iron due to the immense pressure of the rest of the planet pushing down upon it, equivalent to 3.6 million times atmospheric pressure at sea level. The inner core is slowly growing as minuscule portions of the outer core begin to solidify, about a millimeter every year. This freezing is not uniform though, as activity in the lithosphere and the mantle can influence the fluctuation in temperature. However, this growth is so slow that the core will not freeze over for another 91 billion years, which is only a fraction of the time that the sun will burn out in. Due to its isolation from the rest of the layers on Earth, the inner core moves and rotates independent of the rest of Earth. In fact, the inner core completes an extra rotation than the rest of the planet every 400 years. The puzzle pieces. The lithosphere is not a continuous layer of rock, but it is separated into differently sized chunks that scientists call tectonic plates. The tectonic plates are suspended above the viscous asthenosphere. Currently, there are 7 major tectonic plates and countless minor ones that compose the lithosphere. The movement of the tectonic plates is caused by convection currents within the mantle itself. Magma, which constitutes most of the mantle, is a fluid, which allows it to churn around. Magma closer to the core will be heated more than magma closer to the lithosphere, allowing it to become less dense. Objects that are less dense rise through a process known as convection. Thus, magma near the core rises towards the lithosphere before it cools off and sinks back down again. All of the tectonic plates are therefore in constant motion, moving at a rate of about 1.5 centimeters every year. There are 3 types of boundaries between tectonic plates: convergent, divergent, and transform boundaries. Oceanic convergent boundaries occur when a denser oceanic plate sinks underneath a less dense oceanic plate. This process is known as subduction and is responsible for the formation of continental crust. When the oceanic plate subducts, it sinks deep into the asthenosphere, where it melts into magma. Magma is less dense than the surrounding semi-molten rock, causing it to rise. If enough pressure gathers underneath the less dense oceanic plate, the magma is forced out of the earth through an opening in the crust that we call volcanoes. The subduction of the Pacific Plate underneath the Mariana Plate is the cause of the formation of the surrounding Mariana Islands, home to multiple bubbling volcanoes, and the deep oceanic trench that is called the Mariana Trench. Oceanic continental convergent boundaries occur when an oceanic plate subducts underneath a continental plate, forming volcanoes upon the continental crust and a trench underneath the continental crust. Continental convergent boundaries occur when 2 continental plates collide into each other. As continental plates are of the same density, neither subduct. Instead, the 2 plates crumple into a new mountain range. The Himalayan mountain range is the product of the convergence of the Indian and the Eurasian plates. Divergent boundaries occur when two plates move away from each other. When this happens between two continental plates, a rift valley is formed, while when this occurs between two oceanic plates, a mid-ocean ridge is formed. New oceanic crust is created from the magma that rises from the gap in the lithosphere. Meanwhile, transform boundaries occur when two plates slide past each other. One of the most famous examples is the San Andreas Fault Line, which is a roughly 1,200 kilometer boundary between the Pacific and the North American plates. Rumbles and tumbles. While most of the time the ground beneath us remains relatively silent, tempests can rage out of nowhere, destroying cities and infrastructure. When tectonic plates move past each other, enormous pressures build up at the boundaries, more energetic than the most powerful nuclear weapons humanity has ever unleashed. If these plates slip, the accumulated energy travels outwards through the rock in the form of seismic waves, violently shaking the surface in an earthquake. The hypocenter of the earthquake is the point at which the energy is released, while the epicenter is the location directly above the hypocenter, on the surface. Earthquakes are measured based on the Richter scale. A harbor wave, commonly known as a tsunami, is the aftermath of an underwater earthquake. The towering walls of water can drown coasts and even populations further inland. Volcanic eruptions, which are classified based on the Volcanic Explosivity Index, or the VEI, have the potential to devastate entire cities as well. Pyroclastic flows, mud flows, earthquakes, tsunamis, lava flows, ash and aerosol injections, and water acidification can result from the seemingly sporadic eruptions. The largest eruptions in recorded history, such as the 1815 eruption of Mount Tambora, can even cause decades of abnormally freezing periods all across the globe. Although certainly ominous, preparation for these natural disasters have been shown to be incredibly effective. Through efficient humanitarian aid, seeking of shelter, and timely exoduses, the population can be shielded from even the effects of the deadliest earthquakes or super eruptions. Conclusion. The Earth is not a static ball of dead stone, but a dynamic sphere playing a poker game between countless factors, all magnificently acting spontaneously. Occasionally, nightmares of this living planet has the potential to bring about devastating consequences to humanity. Yet, if we maintain speedy procedures against these potent forces of nature, we have nothing to worry about.